All right, more fundamental theorem of calculus problems. At the end of this lesson, you will also be able to evaluate a definite integral using the fundamental theorem of calculus. All right, let's do a few more examples here. On this one, we would like to find the integral of the absolute value of 2x minus 1. I'm actually going to change this problem because I want it to show what I want it to show, if that made any sense at all. So what we are going to do is I'm going to change that to the problem to x minus 1, so if you just change your problem to that as well. Okay, I'm going to do this both by drawing a picture and then using the fundamental theorem of calculus so you can see both ways and actually use which way you like the best. All right, basically this is asking me to find the area under the curve from 0 to 2. I know that this is an absolute value graph, which would be a v, and this minus 1 is going to cause the absolute value graph to shift over one space. So this is what the graph is going to look like, and we would like to find the area under the curve from 0 to 2. So that's what we would like to find. So if I worked on it one way, we could just actually find the areas of the triangles. The triangles. The first one, I could call this A, and this one B. The first one would be 1/2. The base is 1, and the height will be whatever's happening at 0, which is also up at 1. So 1/2 times 1 times 1 would be 1/2. That would be A. And then B, I think it's the same thing, but we'll just double check. 1/2. The base is 1, and the height at when x equals 2, if I plug 2 in there, I also get 1. So that is also 1/2. So 1/2 plus 1/2 will give me 1. So that is an okay to do this way to do this problem. What I'm going to focus on instead is actually using this. We don't have any sort of rule for taking the antiderivative of an absolute value, but please notice where the absolute value v's. It would have been a straight line going down this way, but since what the absolute values did was cause this graph to shift up. All of this stuff on the bottom actually moved up. So it v'd at x equals 1. So what I need to do right here, before I got to x equals 1, my graph would have been negative except for the absolute values bumped it up to positive. So what we're going to do is I'm going to start from 0 to 1, and this original line would have just been x minus 1 dx, and I'm going to actually put a negative in front of that because since this answer would turn out to be negative, since it's below the x-axis, the absolute value is going to bump it above, so that's why I'm making sure I take the opposite of the answer that I'm going to get. And then plus, from finishing it, the rest of it's going to go from 1 to 2. And then we still have x minus 1. And I don't need the absolute values anymore because I've taken care of the absolute value over on the side. Now it's just become a normal problem, actually two separate problems, that I will take the antiderivative of, use the fundamental theorem of calculus, and then add those two answers together. So on this one, if we take the antiderivative of x, I will get 1/2 x squared minus x. And this minus sign is going to go to both parts, so it's actually going to make it negative 1/2 x squared plus x. I'm going to evaluate it at 0 and 1. So plug in 1 first. If I plug 1 in, I'll get negative 1/2 plus 1. Plugging in 0, I'll get 0. So this answer will give me 1/2. Okay, now I'm going to go over and tackle my other problem. The antiderivative again will be 1/2 x squared minus x. I get to evaluate it at 2 and 1. So when I plug in 2, I will get 2 minus 2. And then minus, when I plug in 1, I'll get 1/2 minus 1. 2 minus 2 just gives me 0. And here it will give me minus 1/2 minus 1 is negative 1/2. So that turns into plus. So you'll notice I have 1/2 plus 1/2, which still gave me 1. Now notice, which way did you like better? Totally up to you which way you liked better. They work both ways. All right, let's try another one. This one says to determine the area of the indicated region. So you'll notice we have a picture, we have an equation, but we actually don't have an integral. And I could not use geometry because that is very much an irregularly shaped object. So what we need to do first is write ourselves an integral. This is going to start at 1, end at 2. My function is going to be 1 over x squared, and we'll put dx. All right, so now we get to use the fundamental theorem of calculus to solve this problem. So this will be the same thing as 1 to 2, x to the negative 2. When I take the antiderivative of that, if I increase my power by 1, it will add 1. Negative 2 plus 1 is negative 1. Reciprocal on the outside is still negative 1. So if I rewrite this, this is going to be negative 1 over x. I'm going to evaluate it at 2 and 1. So if I plug in 2, I'll get negative 1/2, and then minus, if I plug in 1, I will get negative 1. Those turn to plus. Negative 1/2 plus 1 is a positive 1/2. And notice that does definitely make sense. I got a positive answer, and my whole entire area is above the x-axis. So hopefully now you can still use the fundamental theorem of calculus to evaluate a definite integral.